is Manuel Alonso García. I'm representing our team. The project is titled Trajectory Tracking System for the PPI quadruped robot using reinforced learning. Okay, let me talk about the objective. Was to implement a comprehensive automation proposal to solve quadruped navigation. We almost designed a system that takes into account the complete interaction of the mechanical structure, the electronic servos, the Rosnoetic software, and cutting-edge control components instead of relying on reliable onboard sensors like emus. Then we implemented a robust vision code. This code is based on the localization system using an overhead smartphone camera using an app named Droidcam app, and a route marker, this one for identify the puppy on the track. For the control, we almost used a soft actor critic or SAG agent with a stochastic Gaussian policy and an automatic target entropy of 2.0 to ensure stable exploration. Okay, now to validate the robustness and the accuracy of our automated system, we almost designed a rigorous testing protocol. We systematically performed exactly 3 physical runs using a traditional PID controller, and we almost do 3 runs using the RL approach. We exported all the vision-based localization and telemetry data in real time into CSV files. By analyzing these CSV files, we generated a Python codes to get the error graphs, and that clearly demonstrated the reinforced learning agent significantly outperformed the PID. The PID struggled with mechanical inertia, whereas our RL agent anticipated the curves, minimizing the lateral error tracking and maintaining a highly stable trajectory. So then let me talk about the simulation. The simulation is on Airbus and bridging the sim-to-real gap. Before the physical deployment, we trained the SAG agent in simulation. We almost simulating on Airbus to validate the policy. However, this transitioning from simulation to really was our biggest challenge. What works in Airbus can damage physical motors. To this bridge the sim-to-real gap safely, we didn't deploy the RL policy directly on the PuppyPie. Instead, we almost used an SAC agent to generate expert demonstrations and applied behavior cloning. This allowed us to deploy a more smooth and cloned neural network to the physical PuppyPie, completely protecting the hardware from the PuppyPie and destructive vibration or hardest movements from the SAC on the first testings. So then, the feasibility constraints and real-world challenge, okay? When evaluating the technical and economic feasibility of this mechatronic development, we strategically analyzed some constraints on the real-world challenge. First, for instance, our overhead vision systems relied on the free version. We are already using a free version of the Droidcam app. We quickly discovered a critical limitation. The app watermark periodically disrupted. The route marker tracking got lost and then generates a temporary data loss. When this happened, we had to intervene and move the robot by hand to recovering on the track. And this manual interference exactly caused some of the student spikes in the tracking error graphs. Clear future improvement, we will to purchase the premium version of the app or maybe have a dedicated camera. However, even with these dropouts, we proved high economic feasibility with this project and the robust robotic navigation on a low budget platform. Okay, now about the conscious entrepreneurship ethics and the sustainability. Finally, we optimally evaluated this initiative from an entrepreneurial ethical perspective. The main people possibility impact of this technology are workers who works in a hard environment, or higher proposed is to replace human exposure to physical risk without these autonomous robots. Furthermore, from a sustainability perspective, our results were outstanding because of the reward function penalized the high power movements. Our early approach achieved a massive 40% reduction. A 40% reduction, yes. About, I don't remember what the exact data, I'm sorry for that, but it's like 40% reduction in total energy usage compared to the PID, dropping from the 6,000 joules to just with the RL we haven't like 3 or 4,000 joules. This is drastically extends the robot's battery lives, reduce electronic waste, and ensuring a highly positive environment impact. So finally, this semester, in summary, we successfully implemented a evaluated highly robust mechatronic system by systematic testing and analyzing real-world data. We demonstrated that our approach vastly outperforms traditional controllers. We achieved this with a strong focus on hardware safety, and then we can get an economic feasibility and a sustainable human-centric purpose. And this is done, I can say. Thank you very much for watching.